Welcome to the deep dive. We're here to extract the key insights from the sources you share. And today, well, we're stepping into what seems like the perfect world of digital logic, clean areas and ones, operations happening instantly. It all sounds very neat, very tidy. But what if that perfect world, it's maybe just an illusion? Okay, let's unpack this. What if the digital systems we all rely on, from your smartphone right up to a rocket, what if they aren't quite as perfectly stable as we think?
That's a really great starting point because, yeah, that ideal model, it's powerful for, like, the initial design phase, but it bumps right up against physical reality.
Yeah.
Hard. Every single component, every tiny wire, it has this inherent delay, a propagation delay. It takes time for signals to travel,
Yeah.
and it's not zero time. It's physics. And the crucial part, these delays aren't uniform. They actually vary quite a bit. And that variability, that little bit of unpredictability, that's really the root cause of almost all the timing issues we see in digital circuits. So today, yeah, we're doing a deep dive into hazards and timing issues in combinational circuits. We'll be pulling insights from the material provided to really get our heads around these critical challenges and why they matter so much for making reliable digital systems.
Absolutely. And our mission, really, for you listening, is to give you that shortcut, to being properly informed about this really fundamental part of digital design. We're talking maybe some surprising facts, definitely practical implications you might not have considered about, well, the digital world that's literally all around us. Okay, so to really get this sort of hidden battle, we first need to look at the gap, right, between the ideal concept and the messy physical reality. Conceptually, a digital circuit is, I guess, elegant, pure. Outputs are just based on inputs right now. No memory, no feedback loops, just clean Boolean algebra. Simple.
Conceptually, yes, perfectly logical, beautiful even. But then you actually build it. You use real stuff, tangible components, silicon gates, ANDs, ORs, not tights, physical wires connecting them. Yeah. And boom, propagation delay enters the picture. It's that finite amount of time a signal actually needs to travel from an input to an output. And here's the kicker, like I said. These delays, not only non-zero, but they are variable. They aren't the same across different gates. They aren't even the same along different paths within the same circuit sometimes. So it's not enough for the logic to just be correct on paper. The timing has got to be meticulously managed too.
And these timing imperfections, how do they actually show up? What do we see? You mentioned glitches.
Exactly. Glitches, they're the most direct sort of physical sign of these timing issues. Think of them as unwanted, temporary, spurious signals, little short duration spikes, or like logic noise popping up where it shouldn't be.
Like tiny unintended flickers in the signal.
Perfect way to put it. Flickers. And the cause, those finite, unequal propagation delays we talked about. See, when inputs change, signals travel along different routes inside the circuit. And because some routes are just physically faster or slower than others, the signals arrive at the next point, say, the input of another gate at slightly different times. This momentary misalignment, this tiny window where things aren't lined up, it makes the output wobble temporarily, deviate from where it should be. Yeah. And even if the circuit eventually, settles down to the right value,
that little flicker itself can cause problems further down the line.
Precisely. It can be highly problematic for whatever component is supposed to read that output next. What's kind of fascinating here is the very existence of glitches reminds us that even when we're designing digital stuff, sometimes we still have to think about, analog characteristics. You often need really high-speed tools like oscilloscopes just to even see these super brief blips. They can be that fast.
Okay, so glitches are the physical blips, but you also mentioned hazards. Are they the same thing or?
Good question. No, they're distinct. Glitches are the effect, the thing you can sometimes see or measure, the consequence. Hazards are the cause. They're the underlying design flaw or the structural property of the circuit that allows those glitches to happen in the first place. A hazard basically signals there's a potential for a malfunction when an input changes, usually just one input changing. The root cause is still those differing propagation delays, but the hazard is the condition in the design that makes the circuit vulnerable to them.
Okay, so the hazard is the vulnerability, the glitch is the symptom.
Exactly, and the impact. It can be significant. Yeah. Even if the circuit, eventually gets the right answer, those temporary glitches can mess things up. But where it gets really critical is in asynchronous sequential circuits. Those are circuits that don't have a master clock synchronizing everything. Yeah. In those systems, a temporary glitch can actually get latched, essentially frozen or remembered or misinterpreted by the next stage.
Oh, wow. So a brief flicker becomes a permanent error.
Precisely. It converts a transient problem into a persistent incorrect state. And that's obviously a fundamental threat to the system's integrity,
Yeah.
especially in anything safety critical. Think medical devices, aerospace.
Right. You might think, okay, a glitch is a glitch, but it sounds like they're not all created equal. You said there are different categories. This sounds like where it gets really interesting.
Absolutely. We usually classify hazards into three main types based on how they behave. We have static hazards, dynamic hazards, and function hazards.
Yeah.
So first up, static hazards. These happen when the output should ideally stay constant. It should be a steady 0 or a steady 1 while an input is changing. But because of those timing differences, it momentarily spikes to the opposite level before settling back down.
Okay, so it should be on one, but it flickers O off F and then back on in. Or the other way around.
Exactly. It's like a 1 goes to 0 goes back to 1 transition, or a 0 goes to 1 goes back to 0. It happens when signals that are meant to kind of cancel each other out or maintain that steady state, well, they just don't arrive at the destination gate at precisely the same instant. And within static hazards, we can break it down further. There are static 1 hazards. Here, the output should stay at 1, but it momentarily dips down to 0. You can almost picture it like, in your design, there's a tiny unintended gap, a blind spot in the logic coverage for keeping it at 1. When the signals race through the wires at slightly different speeds, they can briefly fall into that gap, causing that flicker to 0 before it recovers.
Like a momentary blackout in a circuit that's supposed to be fully powered.
Good analogy.
Yeah.
And conversely, you have static 0 hazards. Here, the output should be steady at 0, but it momentarily spikes up to 1. It's the opposite scenario. The circuit briefly turns on when it absolutely should be O off F. Again, due to timing mismatches and those little logical gaps where the off state isn't solidly maintained during the transition. Okay, second category, dynamic hazards. These are different because here, the output is actually supposed to change. It's meant to go from 0 to 1 or 1 to 0, but instead of a nice clean switch, it oscillates multiple times, unwanted bounces. Like instead of 0 to 1, it might go 0 to 1 to 0 to 1 before finally settling at 1.
Whoa, so multiple flickers during a change.
Yeah, it implies 3 or more transitions when only 2 start and end were intended. It makes the signal look really noisy during the change. These are typically caused by multiple signal paths within the circuit, having significantly different delays, often in more complex multi-level circuits, and they're generally a bit harder to track down and fix than static hazards. You're dealing with a whole series of bounces, not just one quick blip. And finally, the third type, function hazards. Something's called essential hazards. These are special because they only occur when more than one input variable changes at essentially the same time, simultaneously.
Okay, how are they different from the others?
The key distinction is you can't fix them just by changing the circuit implementation, like adding gates or tweaking paths. They are inherent to the logical specification itself. The problem is rooted in the fundamental logic function you're asking the circuit to perform. It means the behavior becomes ambiguous or undefined by definition when multiple inputs shift together.
So it's not how you built it, it's what you asked it to do in the first place.
Precisely. It's a problem with the request, not just the execution. The only truly practical way to avoid function hazards is to basically guarantee that inputs change only one at a time. Which, in many real-world complex systems, that's all just not feasible. So this type of hazard really forces designers to sometimes step back and reevaluate the system's interface or the core logic specification itself.
You really stressed how critical timing is, but what's the underlying mechanism? You mentioned something about a race. What ties these glitches and hazards together?
Yeah, race conditions. They're really at the heart of all this.
Yeah.
A race condition describes any situation where the system's output or behavior depends on the unpredictable sequence or the relative timing of events you can't perfectly control. In digital circuits, this usually means the output of a gate depends critically on the precise arrival times of signals racing towards it. The classic mechanism is signal reconvergence. You have signals starting from the same place, maybe splitting off.
Taking different paths.
Exactly. They travel through different paths inside the circuit, paths with different total delays, and then they reconverge later on, maybe at the input of another gate.
Yeah.
Because they took different amounts of time, they don't arrive simultaneously. So for a brief moment, the inputs to that final gate are inconsistent with what they should be based on the original change. And that inconsistency causes the glitch.
Like two runners starting together, taking different routes, and whoever gets to the finish line first determines the outcome.
That's a pretty good analogy. And if one route has an unexpected delay or they arrive too close together, things can go wrong. A simple circuit example. Think of an AD gate. One input is A, the other input is not A, the inverse of A. Logically, theoretically, A and not A can never both be 1 at the same time. So the AND gate output should always be 0, right?
Right. Makes sense.
But physically. Let's say A changes from 0 to 1. The signal A travels to the AND gate. The signal A also goes through an inverter to become not A, and then travels to the AND gate. That inverter adds a small delay. So if the direct path for A is faster than the path through the inverter for not A, there might be a tiny instant where the original A signal has arrived as 1, but the delayed not A signal hasn't yet changed from 1 to 0. For that brief moment, the AND gate sees 1 AND1.
And the output spikes to 1, even though it shouldn't.
Exactly. That's a classic static zero hazard caused by a race condition. And the really critical impact here, going back to sequential circuits, is the potential to corrupt the state. If one of these glitches happens right when a memory element, like a flip-flop or a latch, is supposed to capture its input, it might capture the glitch instead of the correct value. So a transient, momentary error suddenly becomes a permanent, incorrect state stored in the system's memory. This is what elevates the problem from just, an annoying flicker to a fundamental threat to the entire system's integrity.
Okay, so it all comes down to these delays.
Fundamentally, yes.
Hmm.
Every physical gate, every wire has that finite propagation delay. It just takes time.
But you stressed it's not just that there's a delay, it's the variability, the fact that they're not all the same. That's what creates the chaos, the sort of unpredictable dance.
You've absolutely nailed it. If all delays were perfectly identical and predictable, a lot of these hazards just wouldn't happen, or they'd be much easier to manage. It's the non-uniformity that really creates the conditions for these races. And there are a lot of factors that cause this variability. The way the gate itself is constructed internally matters, and how much load it's driving its fan out. A gate trying to drive, say, 10 other gates will be slower than one driving just 2.
Okay, that makes sense.
Then there's the transition type. Turning a signal on, a 0 to 1 rising edge, often takes a slightly different amount of time than turning it off F, a 1 to 0 falling edge. Even within a single gate with multiple inputs, there can be input-specific delays, because the internal paths from each input pin to the output might be slightly different lengths. And then there are the big ones, environmental factors. Temperature changes things significantly. A chip running hot behaves differently timing-wise than one running cool.
Wow, even temperature.
Oh, yeah. And manufacturing variations. Even on the same silicon wafer, there are tiny, unavoidable physical differences between transistors and wires from one chip to the next, or even across different areas of a single chip. No two are ever perfectly identical. And something that's become a huge deal in modern super tiny circuits is interconnect coupling, or crosstalk. Think of it like electrical interference between adjacent microscopic wires. Signals on one wire can actually affect the delay of signals on nearby wires. It gets really complex, depends on signal patterns.
So the delays aren't even constant, they can depend on what the neighbors are doing.
Yeah, exactly. It adds another layer of uncertainty.
And you mentioned signal splitting and taking different paths.
Right. That leads to what we call asymmetric path delays. This is when a signal starts somewhere, splits, goes through 2 or more different routes with significantly different total travel times, and then they reconverge down the line. A very common scenario is where one path goes through an inverter, or an odd number of inverters, and the other doesn't. The inverter adds its own delay, plus flips the logic. This almost guarantees a timing mismatch when those signals meet up again, setting the stage for glitches. It's like, sending people out of a room, some take the stairs, some take the elevator, and expecting them all to arrive at the next floor at the exact same millisecond. It's inherently challenging. And related to all this timing stuff, we also need to touch on signal skew and meta-stability. Signal skew just means signals, especially really important ones like the system clock, don't arrive at different parts of the chip or different components at precisely the same time. Clock skew is a huge deal in synchronous systems. If the clock tick arrives at one flip-flop noticeably earlier or later than another it's supposed to be synchronized with, you get serious timing violations.
The system basically loses its rhythm.
Okay, so the timing reference itself isn't perfectly simultaneous everywhere.
Exactly. And that can lead directly to problems like metastability. Metastability is this weird, unstable, in-between state that a digital memory element, like a flip-flop, can get stuck in. It usually happens if its input data changes at almost the exact same instant as the clock edge that's supposed to capture it. It violates the setup or hold time rules. Imagine trying to capture a photo of something moving incredibly fast, right at the moment it crosses a line. You might get a blur. A metastable flip-flop is kind of like that blur. Its output isn't a clean 0, it isn't a clean 1. It's hovering indeterminately.
And it stays that way.
It can stay that way for an unpredictable amount of time before eventually, randomly, falling to either 0 or 1. While it's in that state, the rest of the system doesn't know how to interpret its output, which can cause complete chaos or system crashes.
Like-
Yeah. And it's important to see these skew and metastability as slightly different from just path delays causing glitches. They're more fundamental issues of synchronization and maintaining the integrity of the stored state. Violations of timing rules, often exacerbated by clock skew, are a direct path to metastability. It's a critical failure mode, especially for sequential logic. This really underlines why designing robust clock distribution networks and handling signals that cross between different clock domains carefully is so important.
Okay, this is fascinating, but maybe a little scary too. These aren't just like abstract physics problems for chip designers, right? They have real consequences for, well, for you, the listener, and the tech you use daily. How do these timing issues actually impact how circuits behave and ultimately how reliable our systems are?
Oh, the consequences are definitely far-reaching and very real. First off, the most direct impact: incorrect output values. A glitch might be short, but if it's misinterpreted by the next stage, it can lead to calculations being wrong or a system entering an incorrect state it shouldn't be in. Think counter-skipping a number or displaying the wrong value.
Okay, so basic errors.
Right. Then there's system instability. Glitches on critical control signals can cause really unpredictable erratic behavior. Unintended state changes, intermittent faults, those horrible bugs that appear randomly and are almost impossible to debug because you can't reliably reproduce them. The ghost in the machine type stuff.
Nah, the worst kind of bug.
Tell me about it. Thirdly, something people might not think about: increased power consumption. Every time a node in the circuit switches, even if it's an unwanted glitch, it consumes a tiny bit of power charging and discharging capacitance. If you have lots of glitches happening all over the chip constantly, it adds up. It literally wastes battery life in your phone or adds to the energy bill of a data center. Unnecessary switching. And all of this ultimately translates to reduced performance and reliability. Circuits suffering from hazards might need extra time to settle down after an input changes before their output is trustworthy. That means you have to run the system slower than you otherwise could. Repeated dynamic hazards, those oscillations, can even stress components physically and potentially reduce their lifespan over time. And if these issues aren't caught and properly managed in the design phase, they can absolutely escalate to intermittent failures or even complete system failure down the road.
So data corruption, economic costs like recalls.
Absolutely. Recalls, recovery efforts, wasted energy. But the most profound impact, the one we have to take most seriously, is in safety-critical applications. We're talking aerospace, automotive systems like braking or airbags, medical devices like pacemakers or infusion pumps, industrial control systems managing heavy machinery or chemical processes. In these areas, a malfunction caused by a timing hazard isn't just inconvenient. It can have catastrophic consequences: accidents, injuries, loss of life. This really elevates hazard analysis from just, good engineering practice to a critical discipline with incredibly serious real-world implications.
That really drives it home. To make it even more concrete, can you give us some specific real-world examples where these kinds of hidden timing issues have actually caused problems? Where do they pop up?
Sure. Think about digital communication systems. Glitches can directly manifest as bit errors in data transmission. A 1 gets briefly flipped to a 0 or vice versa. This means corrupted files, dropped calls, unreliable network connections. Timing mismatches between the data signal and the clock signal used to sample it are a classic source of errors.
Okay, yeah. Corrupted downloads are annoying.
Exactly. Then, as we just discussed, safety-critical systems. While specific incidents often have multiple contributing factors, undetected timing hazards and control logic have historically been implicated in failures in aviation, automotive recalls, and issues with medical device reliability. The potential consequences there are obviously the most severe. In industrial control systems, a glitch could cause a robotic arm to move incorrectly, a valve to open or close at the wrong time, leading to ruined products, damaged equipment, or even dangerous conditions for workers on a factory floor. Even inside the processor chip itself, in fundamental blocks like arithmetic logic units, ALUs, consider a simple ripple carry adder, which is a basic way to add binary numbers. The carry signal has to propagate or ripple from one bit position to the next. This takes time. The later bits of the sum aren't valid until the carry is rippled all the way through. While not exactly a hazard failure, this inherent delay illustrates how timing fundamentally impacts performance, even in basic computations. Glitches during the calculation could lead to temporary incorrect results before settling.
Other common building blocks like decoders, used to select memory locations, for example, and multiplexers, which select one of several input signals, are also known to be susceptible to glitches. If the signals controlling the selection arrive at slightly different times than the data signals, the output can flicker or briefly select the wrong input. This can cause downstream errors or, again, just waste power. The need to design glitch-free multiplexers is actually a well-known specific problem that engineers work on.
So even standard components have these known issues.
They do. And then just more broadly, across countless digital applications, unaddressed hazards are often the root cause of those frustrating intermittent faults, unexplained data corruption, or sometimes outright system crashes that seem to come out of nowhere.
Okay, let's try to wrap our heads around this. To summarize then, digital circuits, they look simple on paper, maybe like perfect Lego blocks, but the physical reality is way messier because signals take time to travel, propagation delay. And crucially, that delay isn't constant, it's variable. That variability is the snake in the digital garden. It leads to these observable flickers, these glitches, which in turn expose underlying design weaknesses we call hazards. We talked about the three main types: static, flickering when it should be steady; dynamic, oscillating when it should change cleanly; and function, inherent ambiguity when multiple inputs change. And the underlying mechanism allowing all this is often a race condition, where the outcome depends on which signal gets somewhere first. And the ultimate danger, especially in systems with memory, is that a fleeting glitch gets caught and becomes a permanent error, corrupting the system state. A real ghost in the machine. Did I get that about right?
That's an excellent summary, absolutely. Yeah. It's that pervasive nature and the sheer variability of propagation delays, stemming from everything from manufacturing tolerances to the temperature the chip is running at, to complex electrical interactions between tiny wires that really demand these sophisticated design and verification approaches. Those asymmetric path delays, where signals split and reconverge after different travel times, are a prime source of trouble. And things like signal skew and the potential for metastability really highlight how critical precise timing is, not just for speed, but for maintaining the actual correctness and stability of the circuit state, especially when you have different parts of a system running at different speeds or on different clock beats. So yeah, to make sure our digital systems are actually reliable and robust, designers really have to throw a whole toolkit at the problem. This includes using specific hazard-free design principles, sometimes involving adding extra logic, consensus terms they call them, specifically to cover those potential timing gaps and prevent flickers.
So adding gates just to handle timing, not just logic.
Exactly. Redundancy for stability. They also rely heavily on timing analysis and simulation, using advanced software tools, things like static timing analysis or STA, that act like digital X-ray machines. They analyze the design and predict signal arrival times down to picoseconds, flagging potential violations before the chip is even manufactured. Then there are robust synchronization techniques, special circuits and protocols designed to safely pass signals between parts of a system that run on different clocks to prevent skew and metastability issues at those boundaries, plus just generally careful design practices, trying to balance path delays, avoiding certain risky structures like combinational loops, using synchronous resets, the whole discipline. And finally, absolutely critical is thorough testing and verification, rigorously simulating the design under all sorts of conditions, and then once the chip exists, testing the actual silicon with powerful tools like logic analyzers and oscilloscopes to hunt out any remaining real-world timing bugs. It's a multi-layered defense.
So thinking about all this, as our world gets more and more digital, faster and faster, and every single microsecond, maybe even picosecond of timing starts to matter, how does this constant, mostly unseen battle against these tiny glitches and hazards, how does that ultimately shape the reliability, the safety, maybe even the fundamental trust we place in all the technology that powers our lives? You know, from the smallest embedded chip in your kettle to the most massive AI systems processing unimaginable amounts of data, what other invisible physics, what other subtle real-world effects might still be lurking out there waiting to disrupt our seemingly perfect digital dreams?